I am Rajesh Ranganath. I'm from NYU. I'm in computer science and data science, and we're going to talk about out-of-distribution generalization. So to get us started, I'm going to ask everybody a question. And at a high level, this question is more data that makes your training data match your testing data better or worse? So like the top part of this picture is I'm going to take data from one hospital, and I'm going to train on it, and I'm going to evaluate on two hospitals. A and B are just different hospitals. Or I could go ahead and collect data from two hospitals, those exact same hospitals, and then evaluate on both of those hospitals. If you want to make it a little bit more concrete in your head, imagine that I'm trying to take some chest x-rays and classify whether those x-rays have cardiomegaly or pneumonia inside of it. What do people think? Raise your hand if you think one hospital is better. What about, you got a few hands, I see that. What about two hospitals are better? Okay, good. So you can actually do this. So what this plot is just the difference in performance with one hospital versus two hospital. If it goes above this middle line, two hospitals are better. If it goes below, one hospital is better. And the hospital that's being trained on is the first hospital here. It's pretty small. Maybe it's maybe big enough up there. But it's not so important. What you should get from this picture is really that like the answer is sometimes, and that should kind of be surprising. So in about 43% of these examples, actually making the training data look more like the testing data makes it worse. And that should feel really like unintuitive. And it's across like several different conditions, across several different combinations of publicly available chest X-ray data sets. And this is surprising. You know, people's hands were correct that you would a priori be like, if I have more data, I should do better. And generally that's true. And I'm not going to tell you, no, that's not true, because kind of it depends on how you'll use that data. And what's going on here in this particular example is there's quite a bit of variation in the disease prevalence across these publicly available chest X-ray data sets. For something like, we can look at like pneumonia, it goes from like 6% to 2% to 1%, so like 6 times more likely in the MIMIC data set than the NIH data set. And so these models can actually learn to do somewhat well by saying, hey, this data came from the MIMIC data set. If it does, there's a higher chance of pneumonia. Let's say there's pneumonia. And if you only have data from a single hospital, you can't, or a single data set, I should say here, you can't really do that. You can't learn to classify based on classifying the differences in the data that exists. And just a complete view of what I said, we had these two setups where we're training on one hospital, and we asked to evaluate on both of the hospitals. We train on those two same hospitals, asked to evaluate on both. And then oftentimes you see the performance here. Performance is worst group. So like the label in a particular hospital or data set that's the worst is actually getting worse. Okay? And this ties into this like question that I talk about and I've been studying mathematically, which is one of classifying cows versus penguins. So this is like a straw person example where you imagine you train a classifier, you pass it in images of cows and penguins, and you have like a held out test set. You're doing like machine learning the right way. And on this held out test set, you get like 90% accuracy. And you're like, great, I have a really good cow versus penguin detector because I did have held out data that I never saw during training. You evaluated it and you got good accuracy. But then you go in and you pass this image to that classifier. This image is one of penguins, and the classifier will output cows. And the reason it outputs cows is that in the original data set, the background on which the data was collected is super predictive of what the label is. So if you collect a natural, go out in the world, collect a natural data set, penguins will mostly be on ice, cows will be on grass or maybe sand or something like that. And this is a problem in healthcare. We saw it at the beginning where the problem was really like, once I combine data sets together, there's this other signal on like properties of that data set that you can predict with, but you can even see it inside of like existing hip X-ray data sets, where here we're visualizing a representation layer in a convolutional neural net. On the left is a randomly initialized one, on the right is a pre-trained one. And what we can see here is that a priori these representations group in terms of the machine on which the data was collected. So like this green area right here is the X5000 scanner. This red area is the Thunder platform scanner. And if we go all the way to the bottom, we can see that there's like a preference difference in where the hip fractures are. Most of the hip fractures are on the X5000 scanner. And so like if you actually just did the standard machine learning pipeline and you're like, let me take my training data, let me hold out some data, which is a good practice, train a model, evaluate on the model, on the held out data, you can get good performance by just looking at whether the data was collected on the X5000 scanner or not. And then that's true even if you do some pre-training, because the separation is also there on the right. And this actually occurred during COVID-19 as well too. It's hard to imagine, but like relatively early in the pandemic, testing was not widely available. And so people had the idea that maybe we can look at somebody's chest X-ray and determine whether they have COVID-19 or something else. And the way that this went about is kind of like in that example study that was at the beginning, where a bunch of people around the world were loading chest X-rays on GitHub to provide positive examples of COVID-19. And for the negative examples, well, you could just use your old data, right? There's like these publicly available chest X-ray data sets which existed before COVID, and so there's nothing inside of it. And now I have a nice data set. They're positive examples from GitHub and negative examples that come from the existing data. And you know, the authors down here, DeGrave and all, kind of looked at this and was like, hey, this might be a potential for like being able to predict for a reason that we don't expect. And they ran model interpretability techniques, and they found things like the region above the shoulders was important. And like, you know, everybody in this room could probably tell you, like, if I take a chest X-ray and I look at the region above your shoulders, it's not going to tell you anything about whether you have COVID or not. You know, it's outside of your body. And then they went one step further, and they could actually see that if they took the chest X-rays and shifted the locations of the shoulders, the probability of saying COVID-19 would change. And what really was happening was that there was a bias in the data, and some of the chest X-rays that were not COVID-19 people were like aligned all the way to the bottom, while those who were COVID positive, I think they were aligned all the way to the top, meaning their shoulders were as high as possible in the image. And this is a common issue. You kind of would expect it to occur just because of the way that we collect data depends on the perception of a person's health. So if a person is sicker, they might get a portable X-ray because they can't go to like a fancier X-ray machine. And then the perception of the health is also going to be correlated with the thing that we're actually trying to predict or measure. So we kind of expect this to occur just in the natural data collection process. And it appears in other places. You know, we saw the animal example. We talked a little bit about chest X-rays, but also appears in natural language processing, where just there are a bunch of heuristics like overlap in the number of words that might help you make a prediction. But at this point, like kind of without more knowledge, the problem is hard. Even for this like COVID-19 example, I had external knowledge that the machine didn't have. That external knowledge was really that stuff outside the body cannot tell me about COVID-19. The way when we train a machine learning model is like pass in all the data and then hope that that gets learned. But clearly it didn't, and so like my ability to diagnose it comes from this knowledge, and we need to figure out where that comes from. One form of the knowledge that's at play here is that there's some like fixed relationship between a variable we call a nuisance. The nuisance could be like the background in like the cow's image, with the label that's assumed to be static, fixed, for the performance to hold. In the example of cows versus penguins, the fixed relationship is the relationship between the background, like ice or grass, and the label of penguin versus cow. If I move to a data set where I'm getting like all penguins on grass, we'd see a big loss in performance. Another example is diabetes, where the relationship between BMI and the status of diabetes will change in different populations, specifically Asian populations. We're going to try to formalize this mathematically and answer this question, where our goal is going to be to describe a family of data generating processes and then build a predictor that's going to be good regardless of this nuisance label relationship. So in words, we have a label Y, we have a nuisance Z, and we have some features like the chest X-ray X that depend on the label and the nuisance. And this big circle is a bunch of distributions. Different points in it are just different members of that family. So individual distributions where the only difference is the nuisance label relationship. So if we look here, PD prime, the only thing that changes is the distribution of the nuisance given the label versus PD right here. And our goal is to build a low error predictor because we don't know how these relationships will change and we don't know like what setting we will be downstream. So the first idea you should think about is like if I tell you the nuisance label relationship is a problem, like this correlation between like diseases and data sets or like animals and backgrounds is a problem, we should go ahead and break it. And you can break that statistically where the goal is to construct a distribution we're going to call P independent, where what you need to pay attention to is just that the label and nuisance are independent. I'm not going to tell you how to do that or exactly what the algorithmic procedure is for it, but you can just imagine it exists. And then once we have that, we can just try to build a predictor. And here a predictor is just take this distribution P independent and then try to model the label given the features. So like try to train a model on this like hypothetical distribution where you take in the chest x-rays and then predict the label. And this doesn't work by itself. And it kind of doesn't work by itself just for like a textbook reason, something that you might learn in a machine learning class that covers graphical models. So on the left, we have a nuisance varying family where the thing that's changing between the label and the nuisance is just the scalar A. So when A is equal to 0, the label and the nuisance are independent. When A is positive, the nuisance Z is positively related to the label Y. When it's negatively related. And in this distribution, if we break the correlation and then ask, hey, let me try to predict the label given my inputs, it can be worse than chance. And to get some intuition, you can try to look at what the two features are here. The two features are here x1 and x2. One is y minus z, one is y plus z. If z is independent, you basically have that it's just kind of like pure noise. The second feature has a little bit less noise than the first feature, and so if you want to build a good predictor, you want to put more weight on the thing that has less noise. And if you put more weight on the thing that has less noise, you're going to have this like function of z in your predictor, and once I have a function of z in my predictor, you can just be arbitrarily bad. I can just scale a to be larger and larger and larger, and then you're going to be bad. Even though that, speaking in this distribution, the label and the nuisance are independent. And so the question is really like, how can we tell if a predictor will be good? And there are good predictors here. So if we look at x1 and x2, if we add them together, we're going to get 2 times y plus some noise. And 2 times y plus some noise is, you can build a good predictor for y out of that. And so like, what's the signature for it? And the canonical reason of what's going on here is really this like textbook phenomena of like, if I take 2 variables and they happen to be independent, they may not be independent if I tell you a third variable. So if you want to think about that very concretely, if I tell you that y and z are independent, and I tell you their sum, I tell you y plus z, then suddenly the 2 variables have become exactly dependent if there's no noise. Okay? And so we're going to put this idea to work. And so we're going to construct a family of representations such that when we condition on them, the label and the nuisance don't become dependent. And that's what's called an uncorrelating representation. And a representation is simply just a function of the features. So like, I input the chest x-ray, I get out this vector, kind of what we visualized on that convolutional neural net slide. And we can define the performance of the model. The math doesn't matter too much at this point. Probably what you want to get the intuition of is performance is positive, so like bigger numbers are better. And we get our first, I'd say, overall positive result, where for a representation in this uncorrelating set, we can say that the performance is better than chance. So chance is just guessing from the marginal without any features, and this term here is non-negative. But better than chance is the bare minimum of where we can start from. We kind of want to know what is the best representation. And if we assume that we have 2 representations, R2 and R1, and they satisfy this particular conditional independence property, which we call blocking. I'm not going to read it just because it's, again, not too important to follow that as a detail. But you do get that if you have this blocking property, the predictor doesn't actually depend on the representation R1. So in words, if R2 blocks R1, we can write down what the predictor is, and R1 only appears in a term that's a constant that will get normalized out. But like intuitively, what you just want to keep track of is like, if you have this blocking property, knowing R1 does not change the prediction. And you can kind of put this to work like really in a heavy way. There's a lot of text on this slide. I'm going to go through it. What we're going to try to say is like, hey, if blocking is a good idea, maybe if we define this maximally blocking representation, we'll be able to say something good about its performance. And you can say that. So if you do have this maximally blocking representation, its performance is going to be as good as any other representation. That doesn't really tell you how to find it. That criteria was kind of funny, and I kind of didn't even want to talk about it. But we can say that this maximally blocking representation has highest information with the label. And so that gives us a hint on maybe how we might find it. But this sign here is greater than or equals to. So if I tell you that like the information is at least as good as any other representation, you might find another representation that has the same information but worse performance. But 0.3 really tells you that if the information is the same, the performance will be the same. And so like really this concept of blocking will give you the optimal representation in this family. And you can get an algorithm out of it. The algorithm, even though there's a lot of math that went into the step, the algorithm is not too complicated. The first step is actually to construct this nuisance randomized distribution where you make the label and the nuisance independent. You can do it by reweighting, which is the first objective here, or you can also use a generative model to build samples from it. I'll talk about that in a slide in a second. And the second step is that once you have this distribution, build a representation in it. The first term is to maximize the information. The second term is a penalty to keep the representation in the family where there is generalization. Here we're going to penalize joint information instead of the conditional information that you'd expect. I'm going to talk a little bit about that in terms of a plot. But just expanding on the generative bit, just so you get a real feel for like what's going on here, the way that it would work is that you train a generative model to output, say, chest x-rays conditional on the nuisance and the label. The way that you'd construct this nuisance randomized distribution is take your training data, pick a nuisance just at random from your training data set, then pick a label at random from your training data set, pass them both to a generative model, and then produce a new sample. Okay. And you can do this on a toy example. This is just like the example that we saw earlier, where we have a nuisance varying family where one of the features is y minus z, the other feature is y plus z. Instead, we turned it into a classification problem rather than a regression problem. And both generative nerd and reweighting nerd maintain their performance as you change the nuisance label relationship. And they're close to the best linear predictor here, but there still is a difference between training and test. There's a real world, I'm going to air quote real world example here of classifying water birds versus land birds. So water birds appear on water more and land birds appear on land more. So if you're to collect a natural data set, which this is not a natural data set, you'd kind of expect the background to be very predictive of whether there is a water bird or a land bird in the image. If you just take a classifier and then train with ERM, which is like you're minimizing your cross entropy or maximizing your likelihood, your training performance is pretty good, but if you move to a distribution where there are more land birds on water and more water birds on land, the performance drops quite a bit, while for nerd, it's pretty stable. You can do this for pneumonia classification, and you see something very similar. For the performance of just training a model directly, it's pretty good in training, but if you swap to a different disease prevalence, so the prevalence of disease A gets higher in the corresponding other hospital relative to training, the performance drops a lot. For generative nerd and reweighting nerd, the performance is more stable, but it's not good enough to be used. The comment that I'll make is that, from the time that this work was done, which is last year, to today, this probably has changed quite a bit. Like, if you take very large generative models, my guess is that your performance would be stable if you just did something like generative nerd off the bat. And I'll talk a little bit about that in the workshop. So there's a ton of related work here. They're classified in two ways. One is do they support high dimensional nuisances? The other one is, do they require the nuisance at test time? The way that you can classify it in your head is that what I just talked about is the one that supports high dimensional nuisances and doesn't require what they are at test. And so now I'm going to get into a couple of technical bits. So what did I mean by local optima? When I said that penalizing joint information removes some local optima, we should kind of have like a visual intuition for what's going on. If I look at this picture here, we can see that there are like two representations for this example, which is like y minus z and y plus z. One representation is just y plus noise, which is a good one, which is this blue line here. And that does have the highest objective as what you'd expect. Another representation is just z plus noise, and that has a high objective, meaning that it's a local optima, but it's not as high as the other one. The reason that it's a local optima is really just the cost in the information penalty is higher than the predictive value that you get, so the optimization problem becomes trickier. The one way to deal with it might be to anneal this scalar lambda to sort of make the cost balance out, but if you just penalize joint information, you'll get rid of this, but at some cost potentially. And anytime I sort of like change the story on you, like I'm like, well, math says do this, then go ahead and implement something else, you should probably ask the question, did we lose anything? So the conditional version of NERD is going to be model invariant, which means that if I take two different distributions that you train on, the model that you get out is going to be the same. If you have joint independence, which is the stronger assumption, you're going to get risk invariance, which means not only is the model is the same, the quantitative performance would also be the same. And you can actually show that like if you have like these two function classes of representations, then there is going to exist the nuisance varying family where the performance is going to be strictly better for when you have the set of conditionally independent representations. And that just comes from two steps. One is that the uncorrelating set is larger, and two, that the optimal representation is a sufficient statistic, and we show that the minimal sufficient statistic is in the conditional set, but not in the joint set. So the nuisance is an extra variable. Like anytime like you have like extra information, it's kind of annoying. Who's telling me that like the hospital scanner or like the data that I collected from like two different backgrounds is the nuisance? And so we kind of want to have techniques that will help us get around it. And so one thing we can try to do is try to use knowledge of the label instead. And this is an example of a very canonical toy data set called colored MNIST, where you're trying to classify what the digit is, but the color is one of these shortcuts or nuisances by which you can get good prediction but won't generalize if you just shift what the colors are. And if I took these images and I was like, go ahead and permute the pixels. Like I knew that shape is important for digit classification. Took these images and I'm like, permute the pixels. I'll end up with something on the right. Now if I tell you if I'm on the thing on the right and I can predict the label, you might be like, hey, that's funny, right? Like I've like hidden what the structure is, and if I can predict the label, it's probably something nuisance related. And so you can use these data augmentations as a way to, track like surprising things in your prediction. And you kind of saw it happening in that COVID example. Like if you're shifting the shoulders around and you're seeing like, hey, I'm like getting a different prediction, or then you might also have like a idea on how you should augment your data. But you can do this in many ways. You can do this in frequency space. Here's a frequency space corruption for a chest X-ray. It's hard to see, but maybe, yeah, you can still see in like the top left up there, some of the information that's particular to a site is still preserved. And you can also do intensity space corruptions as well too. Like if I know that I'm trying to do something that's heart related, like cardiomegaly, I know that the heart tissue is a little bit brighter, so if I cut out the brighter tissue and I can still make a prediction, I'm in that form of like, hey, probably there's some nuisance-based prediction that's going on. And you can do this with water birds versus land birds, and you'll find that like the performance is about just as good as like knowing what explicitly the background is, whether it's on water or land, like having a human label whether the background is water or land. And just similarly for cardiomegaly, where like knowing like the original like group that the data was collected in, like what hospital, is just about as good as doing these kinds of randomizations or high-pass frequency filtering. And we can do the same thing in natural language. These problems aren't specific to just dealing with images. An example of one is entailment, where we want to know if a premise implies the truth of a hypothesis. Here you have a correct example of the premise was the doctor was advised by the actor, and the hypothesis is the actor advised the lawyer. Sorry, the lawyer was advised by the actor was advised by the lawyer. An incorrect version is the doctor visited the lawyer, and then you say the hypothesis the lawyer visited the doctor. You flipped it, so the inference is incorrect. In these data sets, there are a lot of heuristics. Instead of like thinking about like the background, it might just be the number of common words. So you can do a pretty good job without actually having any understanding of language. And we can see something relatively similar, where like if you take like a baseline method and you're like, hey, your performance is something, if you just use the idea that if I permute my words and can still make a prediction, there's something weird going on, you can get a little bit extra out of it. Okay, so at this point, you should like, if you're paying like really close attention, you should be like, hey, maybe I said something weird. And if we think about this example, which is classifying cows versus penguins, kind of it doesn't matter what the background is. Like if you look at if you look at a face of a cow and a face of a penguin, that will tell you exactly what the label is. So like, why is the background like even playing any role here? And so like, did I just tell you something that like you shouldn't pay attention to or is kind of like irrelevant, or is there something else going on? And just mathematically, like, if the feature is just like if the label is just a function of the features and it's the same function in every distribution, which in this case it is, because the face is always just going to be the same no matter what the background is, then if I just train a model in the way that I learn out of a textbook, in the original data that I have without thinking about anything else I told you, and I could do that well, you should get good performance out. And that's what this equality is here. So do we really need techniques like NERD? Was it just like, did I waste like some number of minutes of your time? Well, first is like this equality only holds if the label is actually a deterministic function, which is not true in several examples. But second, like doing something like NERD isn't wrong. So like if you're like, I'm a big fan of not thinking actually, where it's like you make the methods like as easy and as like simple as you can go, and then you're like, it will work even if you're using it outside of where it is, because like thinking takes effort, and like understanding everything that I just talked about and like owning all the details and using that to a problem is like a high weight task if you're just trying to be like, hey, I'm going to build a chest X-ray classifier that works. But like kind of understanding what went wrong in the first place might give us a different way to solve this problem, and maybe one that requires less information. So we're just going to look at it from a slightly different angle. And I'm going to ask everybody a question again. So here we have like a simple data generating process. So this data generating process, I'm going to describe it in words. There's a lot of math here. The label is just +1, -1 with probability 0.5. The features contain three things. The first feature is related to the label. It's equal to the label actually with probability 0.9. Or probability rho, but just say 0.9. The second feature is the label itself. It is literally like, this like magical logistic regression problem where like the second feature is the label, and so you'd be like, oh, we're great. And the rest of the features are just noise. They're pure noise. They're standard Gaussian distributed. And I'm going to say that I have like, say, 1,000 training examples and maybe a couple hundred features. So I have more training examples than features. And my question is, what do we think will happen when we fit with gradient optimized logistic regression? Anybody have any takes? I'm going to give you an example. One is, because the label is a feature, then logistic regression should just be like, hey, let me put some weight on the label, and then that's the result that you'll find. Who thinks that? So we got one vote here. There's a no vote. That's a good vote, actually, because I'm asking this question. You're voting the right way. And that's kind of the surprise, and this what happens is that like if you do logistic regression here, and this is like a setup that is like, you have more data points than features, and so it's not this like, hey, like there are like lots of different solutions in a very trivial way. You find something funny, which is that like, you're fitting your training data super well. So the training data are the solid lines, and we can see that the accuracy is going to 100% and the loss is going to 0. But the test data, specifically the test data where this like nuisance or shortcut is not equal to label, the performance is just getting worse and worse and worse, and the accuracy is kind of plateaued. Okay, and this kind of feel a little bit funny, right? Because I have more data points than features. One of the features is the label. And then when I did logistic regression that's gradient optimized, I ended up with a predictor that's like doing something very different, even though I have like a feature that's exactly equal to the label. And the first thing to appreciate here is that there are multiple solutions. Even though you have more data points than features, there can still be multiple solutions. So that we should maybe already know that from the plot that we just saw, where we're seeing like perfect training loss, but very bad test performance. And an example of one solution is the one where you just put weight on the label. Another solution would be to take the noise term of a single data point and then make those the weights effectively for the noise components. To get an idea why you could still predict well is that if you were to write down the distribution of the noise and this particular weight term here, W delta, it's just standard Gaussian. So like if I'm placing a weight of 100 on the label and then I'm adding standard Gaussian noise, I'm not going to change the sign. Effectively, you can think that you classify correctly if the sign is positive, and 100 plus the standard Gaussian is just going to be positive. Okay? So which solution gets picked? Like who's telling us how to pick the solution, right? Like gradient optimized logistic regression is outputting a solution, but who's telling us how to get there? And this is where like this idea of like inductive biases come in, and they come in like strongly when you move to deep learning, and that's like the motivation. But like thinking about it in a linear example is helpful because it might help us produce something else. And logistic regression with gradient descent is going to prefer what's called the max margin direction, where it prefers the direction of solution that has minimum norm, where the margin, so like like how far you are, just think about like the predictor times the label, is greater than or equal to 1. And so one good solution is exactly the one we hope for. It's just like put 0 on this correlated feature, that's the shortcut or the nuisance, put 0 on the noise, put 1 on the label. Another solution could be, hey, let's put something that's just on this shortcut and put something just on the noise. To understand a little bit about how that works, I'm just going to say intuition. The math gets a little bit annoying. But so for the examples where the label is equal to this shortcut, the weights that are constructed up here are going to look like the sum of a bunch of mean zero variables, and their standard deviation is going to be like square root the dimension. For those that are in the group where I'll call the leftover group, where the shortcut or nuisance doesn't predict the label, you get something that is like mean order the dimensions with standard deviation root the dimensions. And the key thing to see is that this weight vector is just summing over all the noise vectors for each of the examples that are not predicted well. And so that means that for one of them, this inner product will be big. For the rest of them, it's just going to look like noise. And then once you see that there's like a structural difference, like one is like root D, the other is D, we can try to like separate things apart. And we can be like, hey, there's a chance to classify this. And you can make this all formal with probability bounds. But I kind of like this picture to just sort of visualize this intuition. So this is like you take the logistic regression trained model, and you ask yourself, how well can you classify based on the noise? So when you take the noise in here, you can see for these group of examples that are the leftover, where the shortcut doesn't predict it, you're like, I can predict it super well. Remember, positive numbers means predicted correctly. If I look at the original group where the shortcut does predict, you can predict a lot of them well. Some of them you're doing wrong, but you can correct for it by using the shortcut. So using the shortcut would just squeeze these numbers together, and we can get everything to be positive. And the real connection here is just the connection between loss and margin. Like if we were to just plot the way the log loss looks, as we just increase this margin, like how confident we are, we're just getting more and more value. And so we got this like smooth, monotone decreasing function. And the idea is just going to be really straightforward, is that like, if margin is the problem, if this confidence is the problem, let's just try to build loss functions that penalize them. And one way to do it is just to sort of say, like, make a function that looks like the log loss up to some point, and then make it increase. The mathematical equation is down here, but you can kind of ignore it and just look at the picture. And there are lots of ways to construct these. There are many ways to sort of like have something that goes down and then goes back up. There's like, it's not restricted in any sort of way. But the idea is like in your head, you can be like, this kind of like margin control creates bumpy losses, where the preference is to sort of like make the prediction up to a certain level and then say like, I'm going to stop at some point beyond that. And if I go further, I'm actually going to be like, that's worse. And if you go back to the linear example, your performance will be perfect. And you can actually formally show that it will be perfect for any kind of losses that have this shape. And we can go back to real data, and we can try to study a more challenging setting. And what makes this setting more challenging is that really I'm going to say that I have no idea of what the nuisances are in training or in validation. So a lot of methods that are out there, if you were just going and look under the hood, they will be like, hey, we don't use these nuisances in training, but they use them in validation. And one way you can really do a good job is just like produce a whole bunch of candidate models and effectively select on the validation set, which is just like training just using your validation data. And we look at 3 different data sets. One is Celebrity A, which is classifying hair color as blonde or not. Waterbirds, which we saw in civil comments, is the toxicity of text. And if we look at the test metric as still worst group performance, we can see that all of these margin control methods they're better than what's out there, which was what we hoped for because we really understood what the inductive bias is that leads to these problems. And more importantly, they're about as good as if you give yourself training and validation accuracy. And you'll be validation group labels. And the reason to really pay attention to this in your head is that finding a nuisance is painstaking. I want to say that the thing that keeps me up when I'm working on machine learning for healthcare problems is I take a model, I have good predictions, and I'm are those predictions because of a nuisance? You may be I should just collect more and more data, but in those chest X-ray examples that I started with, I had hundreds of thousands of samples. And so if I'm training a model within just my own hospital, how are you sure? Held out performance for sure doesn't get you there. And so having methods that are geometrically inclined to not do that, and starting with that as a basis is just an easier way for me to think about this. And so there are a few takeaways here. One takeaway is NERD. So you have representation learning for models that generalize as these spurious relationships shift. Another one is that you can use data augmentation to supplement when you may not know what the nuisance is. And the last one is that geometry and inductive biases really play a role in the learning of these shortcuts. And so all you can do from a programming standpoint is you can just change your loss function. We did a lot of work, but in the end, instead of saying minimize cross entropy, you can just say minimize any one of those loss functions that we described, and maybe it's 1 or 2 lines of programming for it if you're using an auto differentiation system. And the references are here. I do want to call out my student, Puli, who was leading the majority of this work. He's looking for a job soon, so please do keep him in mind if you're looking to hire. I'll take any questions if there are.